Hello stormwater designers, and welcome back to Clear Creek Solutions hydrology education videos. Today we're going to be doing an overview of permeable pavement. What is it, what is its purpose, and how is it used in software like EPA-SWMM and wwhm 2012. Permeable pavement is one of the most important low-impact development tools we have today, and unlike conventional pavements which are impervious and shed nearly all rainfall as runoff, permeable pavements are designed to let water infiltrate directly through their surface. This changes the way a developed site interacts with rainfall. Instead of generating rapid runoff that overwhelms storm drains, permeable pavement then stores and filters water within its structure and allowing much of it to infiltrate into the ground or be released more slowly. So in this video, we'll explore how permeable pavement works, the different types available, its benefits and limitations, and why it's considered a best practice in stormwater design. We'll also look at how permeable pavement is represented in two key hydrology models: wwhm 2012, used widely in Washington State for stormwater permitting, and EPA-SWMM, a national and international standard for stormwater modeling. If you're interested, we have a free EPA-SWMM course that you can find in the description down below, outlining how to use the software. It's all contained in a course section, and it has a lot of information and material on how to use the software. So if you're interested in that, check that out down below. So by the end of this, you'll have a clear understanding of how permeable pavement fits into both design and regulatory frameworks. So what is permeable pavement? Well, it's pavement designed to infiltrate water. It refers to a category of pavement systems engineered to allow rainfall and runoff to infiltrate through the surface instead of being diverted as surface flow. The pavement is constructed with open graded materials that create void space, giving rainwater a path downward. Beneath the surface, engineers often include a stone or gravel storage layer, which acts as a temporary reservoir. Water stored in this layer can gradually infiltrate into the underlying soils or be directed to an underdrain. Compared to traditional asphalt or concrete, which functions like a sealed barrier, permeable pavement behaves more like a sponge, capturing, holding, and releasing water back into the ground system. So what are the types of permeable pavements? There are several different types. There are several main types of permeable pavement, each with unique advantages. Porous asphalt looks similar to standard asphalt, but is mixed without fine particles, leaving open voids that let water pass through. Pervious concrete works in the same principle, producing a rigid but porous structure. Interlocking concrete pavers use small gaps filled with gravel or sand between blocks, providing infiltration pathways while retaining strength. Plastic grid systems reinforce soil, grass, or gravel, allowing load-bearing traffic while maintaining infiltration. In practice, designers often select or combine these systems based on load requirements, aesthetics, and cost. For example, a commercial parking lot might use pervious concrete, while a residential driveway might use pavers or grids. What are some of the benefits of permeable pavement? The benefits of permeable pavement extend far beyond simply reducing runoff. First, it substantially decreases stormwater volumes and peak discharges, lowering the risk of flooding and erosion. Second, as water infiltrates through the pavement layers and soils, pollutants such as oils, metals, and nutrients are filtered, improving downstream water quality. And third, permeable pavement helps recharge groundwater and sustain stream-based flows. From a regulatory standpoint, permeable pavement often qualifies as a low-impact development practice, making it useful for meeting stormwater permit requirements. Finally, permeable pavements can mitigate the urban heat island effect by reflecting more sunlight and storing less heat compared to traditional black asphalt. However, it's not without its limits and challenges. Routine maintenance is essential. Without vacuum sweeping or cleaning, sediment can clog the void spaces, reducing performance. Installation costs are typically higher than conventional asphalt or concrete, making cost a barrier for some projects. Structurally, permeable pavements are not well suited to heavy truck traffic or high-speed highways. They're best for light to moderate load areas, such as parking lots, driveways, and sidewalks. Another limitation is site suitability. Permeable pavement depends on soil infiltration. In areas with clay-rich soils or shallow groundwater tables, underdrains are often required to prevent water from ponding in the pavement structure. Engineers must carefully assess these conditions before recommending permeable pavement. So here's how it works. When it rains, water infiltrates directly through the surface layer into a gravel or stone base layer. This storage layer acts like a reservoir, temporarily holding stormwater. From here, water either infiltrates in the native soil, recharging groundwater, or it drains through an underdrain system into nearby stormwater pipes. The result is a major reduction in stormwater runoff, since much of the rainfall never becomes overland flow. In effect, permeable pavement transforms paved surfaces from impervious barriers into hydrologically active systems that function more like natural ground. In the software wwhm 2012, which is the required hydrology model for stormwater design in Western Washington, permeable pavement is modeled as low-impact development. Best management practice. Designers input the type of pavement system, underlying soil properties, and any storage or underdrain layers. Because wwhm runs continuous simulations using decades of rainfall, it can capture how permeable pavement performs over many years of storms. The model calculates changes in runoff hydrographs, allowing engineers to demonstrate compliance with Washington's stormwater permit standards. This makes permeable pavement not just a design option, but a regulatory tool for stormwater compliance. Now, what about EPA-SWMM? In EPA-SWMM, a widely used hydrology and hydraulics model, also includes permeable pavement as one of its low-impact development controls. Engineers can define pavement surface characteristics, gravel storage depth, and optional underdrains. The model requires soil parameters such as hydraulic conductivity and porosity, making calibration important for realistic results. Once configured, permeable pavement can be applied to any subcatchment in the model, allowing users to quantify reductions in runoff, peak flow, and pollutant loadings. By modeling permeable pavement, SWMM users can directly compare scenarios with conventional pavement against LID strategies. Here's an example of some SWMM parameters. When setting up permeable pavement in SWMM, several parameters are critical. The surface layer thickness and void ratio determine how quickly rainfall can pass through. The storage layer depth and porosity define how much water can be held below. The infiltration rate of the native soil beneath the structure determines whether water is absorbed naturally or exists through an underdrain. Underdrain flow properties, such as diameter and elevation, must be specified if drains are included. Finally, engineers input the area of subcatchment covered by permeable pavement. Together, these parameters control how accurately the model simulates real-world performance. Permeable pavement has been successfully implemented in many applications. Parking lots are one of the most common uses since they combine large surface areas with relatively low traffic loads. Sidewalks, plazas, and pedestrian pathways are also ideal. In residential settings, permeable pavement is frequently used for driveways, patios, and small access roads. Some municipalities have piloted permeable pavement on low-traffic neighborhood streets with encouraging results. Permeable pavement is also effective for retrofits, replacing old, impervious surfaces with permeable ones to bring stormwater systems into compliance with new regulations. Designing permeable pavement requires significant attention to detail. First, engineers must ensure the design matches the native soil's infiltration capacity. If soils are too restrictive, underdrains or amendments may be needed. A maintenance plan is also critical, and without it, clogging can quickly reduce performance. Sediment management is essential, since fine particles from adjacent areas can block pores. In cold climates, design must account for freeze-thaw cycles and snow management practices. Finally, designs must comply with local stormwater regulations, which may dictate allowable credit for permeable pavement, design standards, and maintenance requirements. So these are the works we referenced. To wrap up, permeable pavement is powerful, low-impact development practice that transforms paved surfaces into stormwater assets, reduces runoff, improves water quality, recharges groundwater, and helps project meet stormwater regulations. Engineers can simulate permeable pavement in both wwhm 2012 and EPA-SWMM, making it flexible for compliance and design. However, long-term performance depends on the soil conditions, maintenance, and careful design. If you'd like to keep learning about stormwater and hydrology, check out the remaining videos on our channel, where we cover several different topics. If you have any questions, leave it in a comment down below, and check out our free information in the description. Thank you so much for watching, and anyways, we will see you guys next time.